I've focused so far on joint injuries like a knee joint. Of course, problems with cartilage can occur in multiple joints in the body. And the question is, why does that occur? There are multiple risk factors, one of which is the way our joints are loaded mechanically, naturally, just the way we're born. But there are many other kinds of risk factors that could occur and induce an osteoarthritic response in the foot, or in the ankle, or in the shoulder, or the hip, or in the back. The intervertebral disc includes a cartilaginous end plate and other facets of the joint that can undergo osteoarthritic changes. So as we're living older, we're more and more likely to develop this disease. It's estimated now that by the time you get to be 65 or 70, I'll be there in 50 or 60 years myself, at least half of the population of that age will have osteoarthritic problems. Even if they're not painful, if you took an X-ray or an MRI of an individual, you might see these things, and they might eventually evolve into pain. So why does this occur? And what are the mechanisms by which osteoarthritis develops? It's a long-standing issue that people have been studying for 50 or 60 years, if not more. And many groups are approaching this from different angles, from the biology of the chondrocyte to the effects of inflammation. It used to be, in fact, that a while back, osteoarthritis was not considered to have an inflammatory component. But now, in the past 5 or 10 years, it's well agreed upon that inflammation is part of this disease. So are there ways of simulating it? One of the ways in which we're going about it is to take pieces of cartilage, either from animals or from human donor joints that are obtained from hospital. And one can harvest explants, pieces of cartilage, place them into culture. And in a way, I think this is very important, because you could also, if you like, just extract the cells and place the cells into cell culture. And this has been debated for decades. You can more easily discover lots of wonderful things because the cells are easier to get at when they're simply on a plate and not inside a tissue. But in a way, when the cells are inside cartilage, they're in their natural environment, and their response to stimuli, including injurious stimuli, really depends on the cell's natural environment. So what we've been doing, and others in the world have been doing this as well, taking explants of cartilage, placing them into culture, we try to simulate an injury by taking a single explant and subjecting it to a high impact load, which you can do in the lab using instruments that are placed inside an incubator-housed compression facilities. And after this impact load, which might simulate a torque of your knee or something, where you're damaging a bunch of tissues, including the cartilage, we take this injured piece of cartilage, place it into culture, and co-culture it with inflammatory cytokines that are known to be present in the joint, a range of them, IL-6, TNF, IL-1, a range of whatever your hypothesis is, you can try with this model system, carry out that co-culture for weeks at a time, and monitor the degradation of the tissue, which you can do with a variety of different techniques available in the lab. And if you can look at the rate at which tissue begins to degrade, you can then use this incubator-housed system as a platform, if you like, for drug discovery. And so rather than starting with an animal, which obviously has added complications, when we have just a piece of cartilage in the lab, the rest of the animal is missing. And so it makes it easier to study just what's happening in the cartilage. If you then decide that there are some avenues you want to pursue, ultimately you may need to go back to animal models, but starting with this explant in a co-culture environment, you can then study the process of degradation and the ability for drugs to halt that degradation and eventually rebuild the cartilage. In addition to co-culturing with inflammatory cytokines or other molecules you believe might be challenging the tissue, you can co-culture with other tissues in the joint. So some of our students have done co-cultures of cartilage with synovial tissue because it's known that the synovial tissue is a source of these inflammatory molecules, proteins, and so that even further simulates some natural processes that could occur in the joint and allow you to discover where are these challenging proteins coming from. Is it the cartilage alone or other tissues in the joint? The ways in which mechanical injury is applied to the tissue can vary. Sometimes a single direct impact is the problem, but often we can overuse our joints. And so for somebody who's running a marathon, and it's a marvelous thing to watch and to see the folks come across the finish line here in Boston. At the same time, there can be fatigue in a joint and overuse. Some people are more prone to overuse. Some can go through a marathon and recover very quickly. But the continual loading of the joint can create a problem, and that's another mode of mechanical damage that could occur. Not a single overload, but a slight mechanical force which could fatigue the tissue ultimately. So those are the kinds of things that we can also simulate in the lab. And in addition to direct compression, there are shear forces that occur in our joints when we articulate, and those shear forces can be simulated in the lab as well by taking tissue and applying shear to it. So these different ways of combining an engineering approach with trying to understand the cell biology and molecular biology of degradation of the tissue are things that are great to do in an environment like this at MIT. So that's an approach we're using.